Okay, so we are going to study one of the most popular algorithms today. Grover's search algorithm. So essentially, it's a problem of finding a needle in a haystack. So let's say, for example, uh, so of course this was given by Grover, uh, Love Grover, an Indian American scientist. Uh, and essentially the idea is that let's say you have a number to be found in an unstructured phone directory. Let's say all the entries of a telephone directory are jumbled up, and essentially you need to find a particular phone number. So on an average, you have to open the phone directory how many times? Well, half times and over two times. You open the directory once, you find one number, you open the directory. By opening the directory, I mean how many times you will have to consult the directory. You will have to consult it on an average n over two times. So if you're very lucky, you can find it in the first few openings of the directory. If you are really unlucky, then well, you will have to search all the entries of the directory. So on an average n over two times, you will have to find it. So Lovegrover gave a quantum algorithm uh, I think in 1996 to do it in order of square root of n queries. So essentially, uh, mind you, this is not a exponential speed up, but still, uh, it's something which is non-trivial. So as an example, let's say you have 80 Boolean variables. So that means you have 2 to the power of 80 options with, let's say, one correct answer. Uh, so classically you might need 2 to the power of 80 by 2, n by 2 uh, queries. Grover found an algorithm where you can do away with 2 to the power of 40 queries. So let's say at the rate of 10 to the power of 9 assignments per second, basically your computer speed or classical uh, processor, this number of entries is going to take 38 million years. But with the Grover's algorithm, you can reduce this to, assuming the same number of assignments per second, you can reduce this to 18 minutes. This is the quantum algorithm. Grover. So this is, if you look at it, as a tremendous speed up. 18 minutes compared to 38 million years. Um, as a very abstract example of it, or I would say I shouldn't even use the word abstract, but let's say think about the sky and there's an enemy missile coming, and let's say your uh, system has to track that missile somewhere over here, or let's say this is the surface of the earth and there's some sort of a remote sensing application where you have to find a particular point where you are now watching it from a satellite down. So of course these are examples of a spatial search problem, but the concept is pretty much the same thing, that using Grover's algorithm you're reducing the speed or the computational speed to search a particular place where oil might be there or an enemy missile might be there. So this sort of a feature can have some real-time applications, uh, especially in the case of tracking a missile, where the quicker you trap the missile, the better it's going to be, because you have to intercept the missile uh, in real time. So that's essentially the idea. So let's get down to the basics. So what essentially is the quantum algorithm for it? So let's say I give you uh, two vectors. I have a vector u, v, and I have a vector u. And they have some angle between them. And I have another vector psi. So what does a reflection about v, so here's my question, what does a reflection about v followed by a reflection about u do? So if you look at it geometrically speaking, let's see, this is v, this was u, this was the angle theta. You go here, this is the reflection about v. Let's say considering this vector psi was just overlapping with u. So the first reflection is here, and the second reflection, now this vector needs to get reflected about this angle, about u, and that gives me an angle 2 theta, and here's my psi ended up. So that is the second process. So two reflections about two different axes lead to a rotation by an angle 2 theta. Notice in this case we introduce psi to be exactly overlapping with u, but this is not necessary. In general, wherever psi is, it's just going to get rotated by an angle 2 theta, where the theta is the angle between v and u, the vectors about which the reflection was taking place, where theta is the angle between the two vectors v and u. Well, we need to take the order of rotations carefully, but you do the other way around, there might be the rotation about in the other direction, but that sort of is the idea. So now the next question might be, yeah, so by the way, you can try geometrically this for, this was u. You can try this geometrically for any vector psi. So first you will have to reflect it. This is step 1. And then you will have to reflect it by this particular angle. And ultimately, this would boil down to a rotation by 2 theta. So that's always true about a reflection about two vectors. So next we can ask, what operator? So remember, I am representing these vectors as quantum states essentially. So you might ask the question, what operator describes reflection about you? So convince yourself, I'll give you the answer, play around with it. So given an axis or a vector u, this operator describes the reflection about you. So you can ask yourself question, what does u do to the vector u? So, well, the answer is, I hit this vector u, I apply it on u, and this is just going to give me u back again. So a vector reflected by itself with respect to itself is the same vector. Also, you can also show that, so I'll just give you sort of a homework which you can always see. Show that if there's a vector psi which I can express it in components u and w, where u and w are orthogonal, then hitting psi with u is going to retain the u part as we have already shown, and it's going to flip the b part, the w part. So you will get a minus sign over here. Also, you can show u is indeed unitary. So let's go to, with these basics of geometry, let's go to the Grover's algorithm. What's the basic idea? Well, the basic idea is, firstly, as in all quantum algorithms, you have the quantum parallelism step, which essentially is, let me define the vector u in this case as set of all the possibilities, as we did in the Deutsch-Joyce algorithm. How are you going to construct that? Well, you start all states in 0, 0, 0. You apply the Hadamard. So this is the nth thing. And essentially over here, this is the state you'll get. Out here. So for example, for n equals to 3, you'll have x1 to be 0, 0, 0, x2 would be, for example, 0, 0, 1, and x8 is going to be 1, 1, 1. So U is a superposition of all entries of the database. I'm basically enumerating the entire database 0, 0, 0, 0, 0, 1, 1, 1, and so on and so forth. So among all these x of j's, I'll just again write u. Let xi or I is our solution. The particular solution we are looking for. So U is writing as again this guy, and let me use xj and j's interchangeably. So this is this guy, which I can divide as between all the kets which are not the solution and the one ket which indeed is the solution. I'm just decomposing a state which was a superposition of all the entries into something which were not the solutions and something which was the solution. And just juggling of the algebra, what I'll do is that I'll just let me define all the things which were not the solution as a vector v. So what is v? In other words, v is, again, if you look at it, it's just a this thing. So you just do the algebra. V is related to u and I the solution. This was all the superpositions, this was the solution, this was everything but the solution. So now you can see from this equation, this is just a linear combination. U, superposition of all solutions, I, the solution, and V, the complement of the solution, are part of a two-dimensional space, subspace of the entire vector space. The entire vector space. And also notice V is orthogonal to I. Well, one of them are solutions, the other thing is not a solution, so they naturally are orthogonal. So let me say V, this is I, and this is U, my initial starting position, which is superposition of everything, solutions as well as the kits which are not the solution. Now, essentially, the quantum algorithm, the Grover search algorithm, is rather simple. It is the journey of this vector U starting from an initial position, tick, 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 so that it aligns as close to I as possible. Once this vector U aligns with I would have found the solution. So that sort of is the idea. So this is at time t equals to 0. As quantum mechanics involves unitary operators, so on and so forth. So I'm going to design a quantum circuit or a quantum algorithms which is going to take U as close to I as possible. And how do I do that? So again, explicitly writing, we need to rotate U to align as nearly with I as possible. So the technology what we are going to follow is we've already discussed in the basics. This was V, this was I have a U, and I have an angle theta. After the first iteration, what do I get? It's about reflection about two x's. Let's say my initial vector was starting over here, size 0, perfectly aligned with U. The reflection about V and U is going to give me a rotation about 2 theta. This would be psi 1 at t equals to 1. Again a rotation 2 theta, repeating the same process. Now this vector is going to reflect about this vector and then reflect about this vector. Each pairwise reflection is going to cause, and so on. I am going to get psi n, which is going to be exactly aligned or very close to aligned with I, and then when I measure psi n, I am going to recover I, which was the solution. So that's the idea of the quantum algorithm. Essentially, the probability, this guy, gives the probability of finding I. Now the question is, how do we accomplish this? So we already saw a rotation about U. So that is just your vector and if you expand u, remember u was sum over all xj's. If you expand this, this is going to give you all ones matrix with all ones minus the identity matrix. The u, the rotation, sorry, it should be the reflection about u. This is called as the diffusion operator. U is known as the diffusion operator. We'll come to that when we might do random walks. Why is it called the diffusion operator? It just accomplishes a reflection about u, and a reflection about the second step would be a reflection about, let's say, v, and that's going to be accomplished by, let me call it rv. That's going to be again this guy. Notice the resolution of the identity v and the solution I, they form a complete set. It's a resolution of the identity simply because this is all the space of not solution and this is the space of not a solution, and this is a space of the solution. So in some sense you can write v as 1 minus I as well. So RV is nothing but plugging in the value of v from here, identity, or in other words, this is just therefore the unitary is RV is given by let me just write it as RV. So if you look at it, what is RV doing? Let's say there was a state J orthogonal to, all these are basis vectors 1, 2, I, J. They are orthonormal bases. So this operator operating on some J is going to give me just J if I is not equals to J, and this operator operating on J is going to give me minus J if I is equals to J, or I can also then write it as minus I over here. So this is just to give you an example of how to implement this particular unitary. So how does 1 implement this unitary. So let's say I have a bipartite system. So what essentially I want is J operates into the X naught gate Y if J equals to I, and J leaves it as it is if J is not equals to I. So remember, I mean, this gives you an example that the implementation better be a control not operation, because it's a conditional thing. Something else is happening when I is equals to J, something else is happening when I is not equals to J. In order to implement it as a control operation, this is my idea. So now, so let's say this is J, this is Y, and I'll have a control operation, and that control will be on some I, the solution. And this is going to be Y if so this is my circuit if J equals to I, or it is just Y if J is not equals to Y. So this is kind of an oracle problem, and that's why it's called the query model. How many times you'll have to ping this machine? Whenever J is equals to I, the solution, this control not will get activated and you'll get XY, otherwise you get a Y. This is just a way to operate or implement this unitary. And now if we prepare Y in minus state, which is, mind you, the eigenvector of X. So X operator has eigenvectors plus with eigenvalue 1 and minus with eigenvalue minus 1. So if I prepare Y as an eigenvector minus ket, well then what happens? Then this becomes RV J. I can treat it as times Y. This is going to give me minus of J when J is equals to I, and it's going to give me minus of J tensored Y, or minus. It's going to give me J tensored Y, or minus, Y was minus when J was not equals to I, because eigenvector hitting on this X hitting on minus is going to give me minus X, minus of minus. So I'm using over here, so that's the idea. So after this we neglect this qubit and we take the minus sign up. So what happens is the following. We can treat this as this gives you if J was equals to I, and J insert minus if J was not equals to I. Or just focusing on the upper qubit, this is minus J if J was equals to I, and J if J was not equals to I. So these were the two operators. The first operator was, as we have discussed, reflection about U. and second was reflection about V. So geometrically, if you have a V, there's an I, a U, the subsequent reflections are going to make your state land up aligned with I, which was the solution space. So ultimately what you need to do is to keep applying this, the alternatively applying the diffusion operator and the reflection about V operator, so that ultimately you end up, so given an initial state psi, you keep on applying d RV, d RV, d RV, d RV, t times, let's say, to the initial operator u, to get a particular state psi I, psi t, and the idea is that psi t will be very close to 1. The probability is going to, so it will be very aligned to the solution. So alternating between RV, D, reflection about V, reflection about D, which was my diffusion operator, which I also called as so this is U, this is V. I'm calling my diffusion operator, which I defined to be, so I'm using it interchangeably as D over here. These are the same things. So that sort of is the idea. I alternate between U and D, causes the amplitude of the state Y in I to be near maximal, and then I measure this amplitude to find the value of I. So now the question one can answer, we came up with this very elegant method, and essentially it boils down to this is exactly what's happening. You start with a state which is a superposition of all states. By an alternative sequence of rotation about two vectors, you hit something very close to the solution over here. So the entire Grover's algorithm is actually a reflection about two vectors. And alternatingly applying it in sequence, you are able to hit the solution space. Now the question remains how many times you'll have to apply these operators, the sort of the time complexity of this algorithm. So, well, that's also rather easy to figure out. So I'll just again write it as V, U, and I. V and I were orthogonal to each other. U was essentially all superpositions. I was I. So the angle between U and I, that's essentially, if I have to say, that angle is, let's say, cosine theta 2, let me write, that's 1 over root n. The angle between V and U, that turns out to be cosine theta 1, and since these two angles are complementary to each other, they should sum up to be 90. That would turn out to be this guy, because this is also equals to sine of theta 1. So this is theta 2, this is theta 1. So how do I estimate theta 1? Well, theta 1 is, I'll just express cosine theta 1 as a power series. That's going to give me 1 minus theta 1 square by 2 plus some higher order terms. And from the binomial expansion of 1 minus 1 over n, I get that to be equals to 1 minus 1 over 2n minus order of n to the power of minus 2, so on and so forth. So I'll just compare these two things and I get theta close to square root of 1 over root n. So if theta was square root of 1 over root n, and at each time t, I'm rotating by an angle of 2 theta, so I have to cover the angle pi by 2, roughly from here, this end to this end, divided by 2 theta, that's going to give me pi over 4 theta, or that's, because theta was root n, that's going to give me an order of root n improvement. So classically, I was taking n over 2 queries, opening the directory, quantum mechanically using quantum parallelism when I am processing all the states in parallel and then amplifying the amplitude of the solution state, I do it in square root of n times. So that's a quadratic speedup. That we were talking about. So there are several interesting consequences of the Grover's algorithm. One interesting consequence, of course, this is a challenge question. Maybe it's a higher order challenge, but just think about it. Can we do better? So how would you prove that the Grover procedure of quadratic speedup, Grover algorithm, is optimal? Like there cannot be any quantum algorithm which is faster than it. Essentially, quadratic speedup is the best we can do quantum mechanically. Well, it itself is surprising that we can actually, nature has these resources of quantum mechanics that's allowing us a quadratic speed up over a very fundamentally a problem with absolutely no assumptions. See, the Deutsch-Joyce algorithm which we saw, it was sort of a very artificial problem. Either the function is balanced or it is a constant function. We were dealing with Boolean functions and we were kind of getting this exponential kind of speed up. Grover's algorithm makes no assumptions at all. It's a needle in a haystack. A completely unstructured database search gives you a quadratic speedup. Quite remarkable. There are other interesting consequences of this quadratic speedup of square root of n. We'll come to them later, but essentially that's the idea of the Grover's algorithm. See you in the next class.